Welcome to the lecture entitled Scientific Methodology, Problem Solving, Not Truth Discovery. I'm Andrew Chapman. In this lecture, we'll discuss 7 topics. 1. From demarcation to methodology to progress. 2. The threat of postmodernism. 3. Laudan's response to postmodernism. 4. 8 facts about scientific practice. 5. Truth versus empirical adequacy. 6. Science as problem solving. And 7. Theory evaluation as cost-benefit analysis. Since science can't critically examine itself, that's the job of philosophy, science isn't able to answer what is, perhaps, the most important question about itself. That question is, what is science? Answering precisely and adequately the question of what science is requires finding some criterion, some standard or measure that all things that are science meet, and that all things that are non-science fail to meet. Such a criterion would demarcate or separate science from non-science. The search for a demarcation criterion, that is, for a standard that all science meets and that all non-science fails to meet, is at the heart of, and is the jumping-off point for, the history of the philosophy of science, as well as any systematic study of the philosophy of science. The search for a demarcation criterion is known as the Demarcation Problem. Finding a demarcation criterion whose foundations are plausible, that accurately separates fields into science and non-science, and that is possibly employable has proven very difficult. 2 intuitive demarcation criteria known as verifiability and falsifiability quickly fall apart when they're examined closely. Verifiability, which places something's scientific status on its empirical nature, can't possibly be the demarcation criterion because it makes science too empirical to the point that the criterion ends up undermining itself. Falsifiability, which places something's scientific status on whether it produces sentences or propositions that could possibly be proven false, cannot possibly be the demarcation criterion because falsifiability is impossible. Nothing can be falsified by empirical evidence, and this was shown by the Quine-Duhem thesis. Our reason for wanting a demarcation criterion in order to determine the essence or the nature of science is nonetheless an important issue and a worthy project. It's plausible that what separates science from non-science has something to do with a unique methodology possessed by science that isn't possessed by other fields or disciplines or endeavors. So here is a brief historical narrative that recounts attempts to come up with a scientific methodology. First, Bacon's narrow inductivism claims that science is a merely mechanical process and that positive evidence conclusively proves the truth of scientific hypotheses. Then, Hempel criticizes Baconian narrow inductivism by claiming that science is a creative, non-mechanical enterprise and that positive evidence merely raises the probability of scientific hypotheses. Hempel's methodology is known as the hypothetico-deductive method. Third, Popper criticizes the Hempelian hypothetico-deductive method by claiming that even though science is a creative enterprise, positive evidence not only doesn't raise the probability of scientific hypotheses, induction, which is the main logical tool of science, is unjustifiable. Popper's response to Hempel, his falsificationist scientific methodology, claims that good scientists should set out to falsify their hypotheses, and that evidence that doesn't falsify a hypothesis merely corroborates that hypothesis, where corroboration is a neutral status that just means isn't falsified yet. Fourth, Duhem and Quine show, at different times, that falsification is in principle impossible, since hypotheses can never be tested in isolation from an infinite number of auxiliary assumptions. Thus, negative evidence doesn't falsify a hypothesis. It shows that something is false, but it's impossible to ever determine what it is that's false. And then fifth, Kuhn criticizes Popper and pretty much everybody else by claiming that all science is in fact paradigm-bound problem-solving activity, and that scientific conclusions never get science any closer to the truth, because all science is irrevocably infused with the subjective standards bound up in individual paradigms. Thus, it appears that an attempt to find a unique scientific methodology is just as difficult as the attempt to find a demarcation criterion. Fortunately, we can come at the issues of demarcation and methodology indirectly via the issue of scientific progress. The demarcation criterion, the issue of the correct scientific methodology, and the issue of what counts as progress in science are all bound up with one another, such that a solution to any one of these issues reveals the essence or the nature of science, and hence is a solution to the other two issues as well. In the face of Duhem's, Quine's, and Kuhn's critiques of classical conceptions of science, scientific progress, and even rationality, it's tempting to just simply give up on the thoughts that 1, science makes progress at all, 2, science is rational, and 3, that rationality conceived of as a process aimed at objective standards either exists or is epistemically accessible to us, the sort of thing that we could know anything about. And many philosophers of science have done just that. To give up on the notions of progress, rationality, and objectivity is to head down the path of postmodernism. Kuhn officially inaugurated postmodernism in the philosophy of science. There are versions of postmodernism in almost all disciplines. Kuhn had the honor of inaugurating it in the philosophy of science. Postmodernists generally claim that the world that we're talking about, experiencing, and investigating in our scientific and investigative disciplines is intimately bound up with our ways of knowing and representing the world, and these ways have been formed by contingent historical, social, and biological factors that are beyond our control. Hence, a stable and unchanging conception of truth or of rationality that is considered objective in terms of ways of learning about the world have no use in our thinking. Now, if we accept what Kuhn says about the paradigm-bound nature of all science, then we have a decision to make. We could hold to the traditional view that the goal of science is to discover truth and to understand the world as it actually is. If this is the goal of science, then truth and understanding become merely subjective terms, and science becomes a postmodernist project. Or we could reject the traditional view that the goal of science is to discover truth and to understand the world as it actually is. Once truth is jettisoned, postmodernism loses its grip on us. However, we then have the task of figuring out what exactly the goal of science is supposed to be. And just a note here, it's important for us to recognize that almost no contemporary philosopher accepts pretty much anything that Kuhn said. However, direct criticisms of Kuhn are outside the scope of our current discussion. What it's important to see here is that Kuhn historically forced us in the philosophy of science to choose between postmodernism and something else. Enter Larry Laudan. Laudan is a philosopher of science and an epistemologist who's currently a professor at the University of Texas, Austin. His most influential treatise, called Progress and Its Problems Toward a Theory of Scientific Growth, presents a positive theory of scientific progress in the face of Laudan's criticisms of theories known as realism, relativism, and positivism. According to Laudan, post-Kuhnian philosophy is a watershed moment. The revelations of Kuhn and others showed that either we can give up on rationality altogether, that is, we can accept postmodernism, or we can redesign our conception of the nature of science. Laudan thinks that the latter is clearly a better choice, and Laudan actually has a whole bunch of independent criticisms of postmodernism that lend even further support to his decision to steer clear of postmodernism entirely. According to Laudan, previous attempts at demarcating science from non-science and at discovering a unique scientific methodology were blind to actual facts of scientific practice. This is essentially the same claim as was made by Kuhn, and is why Kuhn's criticisms of previous philosophers of science were so powerful. If we're going to redesign our conception of the nature of science, says Laudan, we must first recognize 8 facts about scientific practice and about the history of science. Fact 1. Theory transitions are generally non-cumulative. That is, neither the logical nor empirical content, nor even the confirmed consequences of earlier theories is wholly preserved when those theories are supplanted by newer ones. What this means is that the implicit methodology of science does not attempt to build on past successes. Sometimes new theories add to old theories, but much of the time new theories replace, in part or in whole, old theories. Thus, in reconstructing our notion of the nature of science, we need to take into account the fact that scientific methodology and scientific progress do not aim to preserve the features of old hypotheses or old theories. Fact 2. Theories are generally not rejected simply because they have anomalies, nor are they generally accepted simply because they are empirically confirmed. What this means is that the simplistic picture of scientific methodology is that evidence in favor of a theory is good reason to accept the theory, and that evidence against the theory is good reason to reject that theory. However, the simplistic picture doesn't match contemporary or historical scientific practice. A lot of the time, there are theories that are just contradicted by the empirical evidence or that don't have evidence for them in particular circumstances, and these theories are still accepted. Or sometimes there are theories that have a lot of evidence in favor of them, but the theories are still rejected. So, theory acceptance and rejection is much more complicated than the simplistic picture of scientific methodology would let on. In reconstructing our notion of the nature of science, we need to take into account the fact that there are other issues at play in the decision to accept or reject scientific hypotheses and theories than just anomalies and empirical confirmation. Fact 3. Changes in and debates about scientific theories often turn on conceptual issues rather than on questions of empirical support. What this means is that there is a wide range of considerations that have to do with things like simplicity, elegance, consistency of a theory that are not empirical in nature, but that are nonetheless relevant in how scientists decide which theories to accept and which theories to reject. So, in reconstructing our notion of the nature of science, we need to take into account the fact that it is not just the empirical that is relevant to issues of demarcation, methodology, in progress, but that the conceptual plays an important role as well. Fact 4. The specific and local principles of scientific rationality which scientists utilize in evaluating theories are not permanently fixed, but have altered significantly through the course of science. What this means is that what counts as being rational for a scientist not only differs between different special sciences and different sorts of scientific problems, but these standards of rationality have changed across time. In reconstructing our notion of the nature of science, we need to take into account the fact that different activities that have different standards of rationality can nonetheless still count as science. And so, demarcation and methodology in particular are not tied to one and only one standard of rationality. So, for example, think about Aristotelian science 2,500 years ago. Maybe what was going on 2,500 years ago was very different in terms of the standards of rationality from what's going on now, but we don't look back and say that wasn't science. We say it was still science, it was different. Therefore, any account of science needs to make sense of the fact that different standards of rationality can still be scientific standards of rationality. Fact 5. There is a broad spectrum of cognitive stances which scientists take toward theories, including accepting, rejecting, pursuing, and entertaining. Any theory of rationality which discusses only the first two will be incapable of addressing itself to the vast majority of situations confronting scientists. What this means is that traditional and simplistic accounts of scientific methodology and progress took it that scientists only accepted or rejected theories and hypotheses. However, scientists do much more than just this, and as such, the picture of what scientists are up to with respect to evidence, methodology, and progress is much more complicated and nuanced than was traditionally thought. In reconstructing our notion of the nature of science, we need to take into account the fact that the methodology of science seems to be aimed at goals other than just finding the single correct theory, and, as such, what counts as scientific progress can't be analyzed merely in terms of the truth or falsity of hypotheses or theories. Fact 6. There is a range of levels of generality of scientific theories, from laws at the one end to broad conceptual frameworks on the other. Principles of testing, comparison, and evaluation of theories seem to vary significantly from level to level. What this means is that traditional and simplistic accounts of scientific methodology and scientific progress took it that there was only one kind of thing at one level of generality that scientists investigated. However, scientists investigate the world at many different, often overlapping levels of generality. Thus, the picture of what scientists are up to with respect to evidence, methodology, and progress is much more complicated and nuanced than was traditionally thought. In reconstructing our notion of the nature of science, we need to take into account the fact that the methodology of science encompasses things at many different levels of generality, and, as such, what counts as scientific progress can't be analyzed merely in terms of the investigation of one sort of thing at one level of generality. Fact 7. Given the notorious difficulties with notions of approximate truth at both the semantic and epistemic levels, it is implausible that characterizations of scientific progress which view evolution toward greater truthlikeness as the central aim of science will allow one to represent science as a rational activity. What this means is that the traditional and simplistic picture of scientific progress held that science progresses when its hypotheses and theories got closer to the truth. However, what it means for something to be closer to the truth than some other thing is very unclear, even though that's a concept that we use in everyday conversation. Two false propositions are equally false. How could it be that one of them is closer to the truth than the other? And even if this seems like an intuitive concept, being closer to the truth than something else, once you try to analyze this concept to make sense of it, to say what the conditions are for something to be closer to the truth than something else, things get very hard, if not impossible, very quickly. Therefore, in reconstructing our notion of the nature of science, we need to take into account the fact that since nearly impossible to discover or outright incoherent, what counts as progress in science can't be analyzed in terms of getting closer to the truth. And fact 8. The coexistence of rival theories is the rule rather than the exception, so that theory evaluation is primarily a comparative affair. What this means is that the common sense picture of scientific methodology is that theories are compared directly to reality in order to tell whether the theory is a good one or not. But in actuality, theories can't be compared directly to reality. That thought is, in fact, incoherent. But theories can be compared to other competing theories. The theory that is chosen when two theories are compared to one another is the one that is better between the competing. Thus, in reconstructing our notion of the nature of science, we need to take into account the fact that scientific methodology and progress are determined by a comparative cost-benefit analysis between competing hypotheses or theories, and not by comparing a theory or hypothesis directly to reality, whatever that would mean. Now, we need to admit, says Laudan, that we have no way of telling when some theory is actually true rather than when it is merely empirically adequate, where empirical adequacy is when a theory appears as though reality is in line with that theory. The concept of truth is about reality, while empirical adequacy is about the evidence that we have, and we can't ever get behind our evidence to see how reality is on its own terms. Evidence is what stands between us and reality. Accordingly, if scientific methodology had ever been about discovering truths, or if scientific progress had ever been about having more true theories, then science would be impossible, and science would never have made any progress at all. However, science isn't impossible, and science has made progress. Thus, science must never have been aiming at truth. Instead, what science must have been aiming at is achieving some goals that it's possible for us to tell when it achieved. To see why Laudan thinks that we ought to jettison the concept of truth when analyzing scientific progress, consider the many different and mutually contradictory interpretations of quantum theory. At most, one of them could be true. However, we have no way of telling which one is true, since each one of them is completely in line with the empirical evidence. That is, each one of them is empirically adequate. What we can tell is whether adopting one of the interpretations over the others gets us closer to achieving the sort of thing that we want to achieve in some particular circumstance. Says Laudan, only by setting goals for science which are in principle achievable and which are such that we can tell whether we are achieving or moving closer to achieving them, can we even hope to be able to make a positive claim about the progressive character of science. There are many non-transcendent, immanent goals in terms of which we might attempt to characterize science. We could view science as aiming at well-tested theories, theories which predict novel facts, theories which save the phenomena, or theories which have practical applications. My own proposal, says Laudan, more general than any of these, is that the aim of science is to secure theories with a high problem-solving effectiveness. From this perspective, science progresses just in case successive theories solve more problems than their predecessors. Just to sum up what's being said here, if we set goals for science which science can't achieve, or which we can't tell if science is achieving, then we're not going to be able to practice science. If we set goals for science, like solving problems, and we can tell when science has achieved those goals, solved those problems, then we can make progress with science and we can tell how to do science when we set out to achieve those goals. Now, if the goal of science is solving problems, as Laudan says it is, that is, if scientific methodology tells scientists to solve problems, and that is, if the more progressive or progress-making theories are those that solve more problems than do their rival theories, then we need an account of what a problem actually is. And of course, Laudan has left this concept of a problem very broad so that it can encompass a number of goals that we might set for science. According to Laudan, there are two broad sorts of problems that science sets out to solve. The first is empirical problems. These are problems with empirical consequences, consequences that we can see or smell or touch or hear or taste, such as why X behaves a certain way, or why Y produces such and such experimental result, or why Z is found in some places in the world but not other places in the world. The second sort of problem is conceptual problems. These are problems internal to the theory itself and between theories, and they don't have empirical consequences. Conceptual problems might be whether such and such a theory is internally consistent, that is, whether it contradicts itself or not, whether the theory is in line with other accepted scientific theories, or whether the theory makes use of currently accepted logic and mathematics, or whether it's revisionary. When evaluating potential theories in order to determine which theory is more progressive and hence which theory we ought to choose, Laudan says that we need to run a cost-benefit analysis with solved problems serving as the benefits in the analysis and unsolved problems serving as the costs. Such an analysis would consider both the number of problems that are solved and left unsolved by a theory and the relative weight of those problems. Some problems might be more important than other problems and so might have more of a weight in the cost-benefit analysis. Here's a somewhat complicated example. Let's say that theory 1 solves 10 empirical problems and leaves 2 empirical problems unsolved while solving all of the conceptual problems on the table. Theory 2 solves 12 empirical problems, leaves no empirical problems unsolved, but leaves 1 conceptual problem unsolved. Then, depending on the weight of the different problems left solved and unsolved, either theory 1 or theory 2 will come out as more progressive, solving more problems. For example, if the unsolved conceptual problem from theory 2 is that it rejects all of modern logic, that would be a high price to pay for the solution of 2 more empirical problems. But if the unsolved conceptual problem is that theory 2 rejects some components of some other accepted theories, well, that might be an acceptable price to pay. Now, of course, determining the actual cost-benefit analysis that we should use is part of the scientific enterprise itself, and it's a task for which philosophers of science are uniquely skilled. Laudan's theory is revisionary and somewhat complicated, so here are the bullet points. According to Laudan, the best option for saving the rationality of science from postmodernism is to claim that the concepts of scientific rationality and scientific progress have nothing to do with the project of discovering truths about the world. The history of science and current scientific practice seem to support the thought that scientific methodology and progress are not determined by truth-seeking. There is no difference from our perspective between a true theory and a theory that is merely empirically adequate, that is, one that's in line with all of the empirical evidence. Science is rational and makes progress according to Laudan when it solves problems that we set for it, and when those problems are ones that we can tell when it solves. There are 2 broad sorts of problems: empirical problems and conceptual problems. And when evaluating a theory, we compare it to rival theories via a cost-benefit analysis to see which theory solves more problems. Since Laudan's theory is revisionary, it has some unexpected implications, or at least some non-traditional implications. Laudan comes at the issue of the nature of science via the issue of scientific progress, and this is a somewhat unique methodology in the philosophy of science. Many philosophers of science come at the issue of the nature of science via either the demarcation problem or the issue of scientific methodology. The traditional picture of science as helping us understand and explain the natural world is completely lost with Laudan's theory. Science is now a purely practical endeavor, one with no time for such transcendent goals as truth. So when evaluating Laudan's theory, we'll need to see whether we're willing to throw out the traditional goals of understanding, explanation, and truth. Laudan thinks we have no choice. And since even non-scientific pursuits solve problems, for Laudan, according to his theory, there's no sharp distinction between science and non-science. And what that means is that there's no clear demarcation criterion for Laudan. Something might be more or less scientific, but it's not as though there's a set of criteria that all things that are science have and that all things that are non-science fail to have. In this lecture, we've looked at 7 topics. 1. The move from demarcation to methodology to progress. 2. The threat of postmodernism in the philosophy of science. 3. Laudan's response to postmodernism. 4. 8 facts about scientific practice. 5. Truth versus empirical adequacy. 6. Science as a problem-solving endeavor. And 7. Theory evaluation as a cost-benefit analysis. Thank you.